So this is an example where we have what's called a pneumatic spring. Another way of looking at something like this, you may have seen gas-charged cylinders before. Some people might have these. Say you've got an SUV or something that's on the back of your on your car that holds up the maybe hatch on the back of your car, something like that. This is a similar kind of thing. This one is set up so that there's a charge of air trapped inside of this cylinder. And there's a tube actually that allows air to flow from one side to the other. You see that tube over there. Well, for this particular one, it's got a certain amount of force that's holding the piston in the position that's shown. And as a result of the internal pressure that's inside the cylinder, we are able to read on the outer surface of the cylinder using a strain gauge. We're able to read a strain value in the tangential direction of 40 micro. Okay, now that we've seen that before, but micro basically just means times 10 to the minus 6, right? So it's just another way of writing strain values that we use fairly frequently. Okay, we're going to assume 0 seal friction, and what I want to know is, based on this 40 micro of strain that we're measuring, how much force must be applied to the cylinder on its ends, F, that's holding the thing in. Okay, so I'll go ahead and say that may not be a realistic idea that the seal friction would be 0, but if these forces are high, then it might be something that's a possibility. The seal friction is relatively insignificant compared to the forces that the other forces that are involved. So, all right, here is kind of the big idea as to why this problem's kind of maybe a little trickier than you might have otherwise thought. If you go into this set of notes that we looked at earlier in the quarter, you might remember that we had some equations here, and I'll go ahead and say that for our problem, where that strain gauge is applied, it is in a state of plane stress. How do I know it's in a state of plane stress? It's on the outside surface, and there's no significant forces being applied. You know, you might say ambient air pressure. That's going to be a pretty insignificant force relative to everything else that we're dealing with. So we're going to basically say that there's plane stress going on. And you might remember that in this, in these notes, we had a case of plane stress, and we've said that the strain that happened in a particular direction is going to be equal to 1 over the elastic modulus times the stress happening in that same direction minus Poisson's ratio times the stress happening in the opposite direction, or in the kind of the perpendicular direction. I'll mention this too. One of the reasons this works is that I can inspect our original problem and notice that there's no shear being applied in this, no shear being directly applied in this. In other words, it doesn't have something like a transverse shear from bending, and it doesn't have something like a shear applied from torsion, right? There's no shear that's going to be applied where that strain gauge is being applied, which means that it's in a state of plane stress, and we are getting one of the principal strain values from the strain gauge. Okay, see that so far? We're getting the principal strain value in the tangential direction. All right, so let me go ahead and write down what that, equation said just a second ago, but I'm going to write it in terms of the tangential direction and maybe another direction. So I would say that the strain in the tangential direction is just going to be equal to 1 over the elastic modulus times the stress in the tangential direction minus Poisson's ratio times, and this is the other component of stress that matters in this problem, it's a longitudinal, and I'll kind of denote that with a little subscript of L, okay? So for this problem, tangential is basically the direction that goes this way, and longitudinal is a direction that goes this way. We're not measuring longitudinal, we're only measuring tangential, okay? So this is L and this is T, okay? And what we're measuring is basically this value out here. And what we're measuring, though, is not a function only of the tangential stress. It's going to also have some of the longitudinal stress built into it as well. All right? So here's what I'm planning on doing. I'd like to go into the text and say, okay, so far so good. Let's find what we've got for our tangential stress. Okay, and I'll do this for the outer surface. Okay, at the outer surface, the R factor that's in there is just going to be equal to the outer radius. So in other words, that general radius that's in this function we're about to write is going to just be equal to that outer radius. And here's what they have in the text, equation 350. Okay, it says that our tangential stress is going to be equal to the inner radius squared times the internal pressure P sub I over R sub O, right, that's the outer radius squared, minus R sub I squared times 1 minus, excuse me, not minus, plus, I was looking at the wrong one there, plus RO squared over, originally they had R squared right here. What do we need to do when we're doing the outer surface? Okay, plug in an RO in for that factor right there because we're on the outer surface. Okay, so what this gives us is a way to relate the internal pressure inside of this thing, which, by the way, the internal pressure inside of it is going to be related to how much force you're applying to the ends. But it allows us to relate that internal pressure to the tangential component of stress that's going to be carried in this body. Can we do that for the longitudinal direction as well? Okay, my hope is that we can. Longitudinal. Okay. In the longitudinal direction, though, it's very tempting for us to look in the text at page 128. There's an equation there, 351. Okay. And it says pi ri squared over ro squared over ri squared. Here's what's tricky about that. It's actually relatively easy for us to go in and figure out how they got this equation of the pi ri squared over ro squared minus ri squared. It's really just based on a free body diagram of a portion of a cylinder that's been chopped off and then forces summed along the axis of the cylinder. Okay? And so built into this expression right here is the idea that you have a full-sized end cap, all with pressure on the end of it, right? And that's going to be what generates those internal longitudinal stresses in the part. Is that what we have? No, ours is different because I have this seal with a rod through the middle of it, right? In our case, the only internal pressure that creates this longitudinal stress is going to be based on that pressure being applied to this little ring, right? And we're going to eliminate the area where the rod is located. We're only going to look at where that pressure applies to that ring. Okay? So I'll tell you what I'm going to do. Instead of using their equation without thinking about it, what I'm going to say is let's go ahead and cut, right? We're going to make a cut and look at just the cylinder to the left, okay, of where this cut is made. And let's actually take a look at that as a free body diagram. Okay, so I'm going to do a little sketch right here. Okay, and I'm drawing it, kind of showing that I've made a cut. Okay, there's going to be the little end of it that I've chopped off. But inside of here, there's going to be, kind of that back wall, right? And then there's the place where the rod goes through. And my point is that what we're doing here is we're going to look at stress that's applied this way in the cylinder wall. Okay, and I'm just going to call that sigma sub L, right? That sigma sub L is caused by there being internal pressure being applied to that little ring that I mentioned earlier. Okay, that's my P sub I. Okay. And what are the sizes of the different, parts of this? Like, in other words, if I was going to, talk about the radius to the outside, okay, What would I call that? Would that be RO? Right? What about to the inner wall right here? Would that be RI? Okay. And I need another one, though, too, because I also have a little radius value where that rod goes through. So let me call that R rod. Okay, so I've got all these different R values here. And what I'm going to do is sum forces for this thing along the axis of the cylinder itself. And when I do this, let me take the stress that I have in that longitudinal direction, and to turn it into a force, I got to multiply by an area. So the area that I multiply by is based on pi r squared, but since it's, you know, kind of a ring, and I'm going to be looking at this, the area of this little ring shape right here, right? Just that much area, it's going to be based there on RO squared minus RI squared. Okay? And then in the other direction, from the direction of the stress that's induced in that cylinder wall, I have, so I'm going to put a minus because it's the other direction, I have the internal pressure P sub I times the area over which it acts. And what's that area going to be? Pi times what? Okay. RI squared minus R rod squared. Okay? Because the internal pressure isn't actually acting on an end cap where we have area right there, right? There's a rod that goes through the middle of it that eliminates that as some of the area that needs to be considered. Okay? So I've got to change up my longitudinal stress. That's what I'm doing with this whole thing, is changing up my longitudinal stress because I don't have just a plain cylinder. Right? The other way you could do this, by the way, if it's a little bit harder to do, but you might notice that on the other end of the cylinder, I have pressure pushing against that back wall, this wall right here, right? I've got pressure pushing against there, but some of that pressure is going to be offset by the force of F. And the difference between the force acting on this face right here and F, right? The difference between those two is going to generate the same stress in the cylinder wall, right? On this end, though, I don't have to deal with F because all I have to deal with is just the pressure that's acting on this little annulus. Does that make sense? Questions? Yeah.
The tangential stress equation?
Yep. Did I miss something in the tangential stress equation?
Was that in the PDF? Or,
This is in the text here. They dealt with this, and it's equation 350.
and why was it RO squared over RO squared?
Because we're going to plug in RO, or R equal to RO, right? And this value right down here started out being R, right? But now it's, you know, plugged in a value of RO, okay? Based on equation 350 in the text. All right, so back to where we were here a second ago talking about longitudinal stress. This takes care of the forces acting along the axis of this cylinder, and I can now, you know, kind of collect different things here and say, for instance, sigma L is just going to be equal to pi times Ri squared minus R rod squared, okay, all over pi times RO squared minus RI squared. Okay, and you'll notice there the pi divides out, and you have something that's similar in form to the equation that they have, equation 351. The only difference is that for us, instead of just having Ri, we have IRI squared. We have Ri squared minus R rod squared. Okay, and that's the effect of the fact that I've got that rod coming out the middle of it. Okay, so there's that. And what do we do with it? We can substitute. okay? We'll substitute into my original equation up here. So my tangential strain now is going to be equal to 1 over the elastic modulus times, all right, here, let me actually kind of simplify this a little bit. 1 plus RO squared over RO squared, that's just 2, right? It's 1 plus 1, right? So I'm going to take that over here and just say 2 times RI squared PI, oh, not squared on the P, over RO squared minus RI squared, okay, minus Poisson's ratio. So I'm going to go now to my longitudinal stress. Poisson's ratio times P sub I times RI squared minus R rod squared. Okay. And then that's going to be over RO squared minus RI squared. With me? Now, can I solve that for P sub I? It's not that hard because P sub I can just be factored out. And when I do that, P sub I is going to be equal to the elastic modulus times the strain in the tangential direction, okay, times RO squared minus RI squared. All this over 2 RI squared minus Poisson's ratio times RI squared minus R rod squared. Okay? Now, we can solve, because everything to the right there are things that we can easily find, right? So we go up here, we remind ourselves, I know the dimensions. A is 40 millimeters, B is 75 millimeters, C is 50 millimeters. I know the material is 18-8 stainless steel. 18-8 stainless steel has an E value based on table A5, has an E value of 190 GPa. Okay? So I'll tell you what, I'm going to start populating this. P sub I is going to be equal to 190 times 10 to the 9th newtons per square meter. That's what a gigapascal is, 10 to the 9th Newton per square meter. I have 40 times 10 to the minus 6. That's what 40 micro strain actually means, and that is unitless. Okay, and that's what we got out of our strain gauge in the givens in the problem. RO is based on the outer radius, and I believe I said the outer diameter, right, was 75 millimeters. So for that, I need to take 75 millimeters, which is just 0.075 meters over 2, and that'll be squared, minus, and I believe the inner diameter was going to be 50 millimeters, and that just gives me 0.025 meters of radius, and that'll be squared. Okay. In the denominator, I have 2 times, again, 0.025 meters squared, minus, okay, table A5 in the back of the text has Poisson's ratio to be 0.305. Okay. And then, again, I have RI, which is going to be 0.025 meters squared, minus R rod, okay? And that is just going to be based on the diameter of the rod, which is this A. So the radius of the rod would be 20 millimeters. So here I'm going to put 0.02 meters squared. Okay? And I'll spare us actually punching all of that in. Hopefully you believe me when I say this calculates to 5.026 megapascals. Okay, which is a lot of pressure. Right? I heard someone say it's a lot of pressure. That is a lot of pressure. Okay, that's not actually what the question asked for, right? What did the question ask for? It wants us to find the force carried in the spring. Is that related to the pressure? How so? Okay, pressure is equal to force over area. Now I'll say, for a lot of folks, they're tempted to want to figure out, well, I've got pressure that acts on the back side of this piston. I've got another pressure that acts on the front side of this piston. And then I've got, maybe that's all that they would look at is those two pressures. Okay? Let me show you an easier way. Anytime you have a situation like this where the pressure is the same on both sides of a piston like this, you don't really necessarily need to look at the piston, because what you can look at is what is the actual swept volume, right? How much volume change, what's the area that causes volume change inside of this vessel, right? What is that area? Yeah, so in other words, if this thing was to move in and out, what's the area that you would use along with the distance that it moved in and out to think about volume change? Yeah, you'd look at the cross-sectional area of the rod, not really of the piston. And it makes sense. You can actually do that out if you'd like, but you can take the area of the kind of the whole face of the piston minus the area of the ring, and that gives you the area of the rod. Like you can do that out mathematically, or you can just say that's the area that the change in volume is based on as it changes in length, right? So all that to say, what you do with this pressure now to find force, okay, you take that pressure, P sub I, and you're going to multiply it by the area, cross-sectional area of the rod, pi times r rod squared. And this is going to be equal to the force. Okay, and so in here we'll plug in 5.026 MPa, okay, multiplied by pi times 0.02 meters squared. Okay, and when we punch that in, it ends up giving us 6,316 newtons. Okay, or if you prefer to see that in kilonewtons, obviously that's 6.316 kilonewtons. Okay, so a couple of big takeaways here. One is be very careful with your longitudinal component of stress, right? If you have plain old end caps, you can use the equation that's in the book. If you got something else different like what we have here, maybe it's not worthwhile, or maybe it's not actually legitimate to look at the equation that's in the book. Okay, so but it is one of those things that you can pretty much always go in and calculate it if you know enough about the geometry, right? You can kind of do a free body diagram and calculate it. The second thing that I will say is, as a big takeaway, notice, so that we don't miss the forest for the trees here, notice we can look at data from a strain gauge like that, and it can give us information about some of the other loads that are in the system, right? We based really the only piece of information beyond what kind of material we've got and some of the dimensions, the only information we had about loading was that strain that we were able to read off of the strain gauge, right? But then we're able to relate that to how much force is being applied to the spring. Yes, sir?
Why did you use the radius of the rod and not the radius of the inner tube?
Okay, the reason I used the radius of the rod for that last step is that is what I'm calculating here. That is the amount of area that sweeps if the piston changes length, right? If that pneumatic cylinder changes in length, the amount of volume change is based on that length that it would change times the area of the rod. See that? For the other area, of the piston, it's kind of irrelevant because you're not changing the amount of volume that's stored inside of the system, right? Just by moving the piston back and forth. The only thing that changes the amount of volume in the system is the fact that you've got rod either moving in or out. Does that make sense? So that's what I was trying to explain earlier. You could also get to the same conclusion just by looking at the pressures on both sides of the piston. That would end up telling you the same thing. You'd have to take the area of the full piston and subtract the area of the ring that is not the rod, and that would end up giving you the same conclusion for the force. All right? Good deal. Other questions?
So you're saying that the cross-sectional area of the rod, if they were to increase or decrease, that would more directly affect the pressure inside the spring?
So the area of the rod and the fact that it moves is what changes the volume of the spring, right? And so it's, that is the thing that is going to relate the amount of force to the amount of pressure. Again, that's something we could prove. I wasn't planning on sitting here and proving it this time. If you don't like that, you say, I don't, that bothers me. Let's do it the other way, okay? We'll say F instead is equal to your internal pressure times pi times your RO squared. Okay, that's pushing one direction, minus your internal pressure times, not RO, RI. Okay, because basically what I'm looking at is the size of the full face piston. It's going to be based on RI, okay? And I could say that minus PI times pi times RI squared minus R rod squared. Would you agree that's another way I could go about doing this and saying I'm really just going to look at the force acting to the left because of pressure on the right side of the piston, right? And then the force acting to the right based on the left side of the piston, right? And I get that force. And that's what it would be. Well, I can factor out the PI and the pi, right? PI, pi. Here I have RI squared minus RI squared minus a minus R rod squared. Which is PI times pi times R rod squared, which is what I had before. Okay? So, believe it or not, what we did a second ago in terms of like figuring out the swept volume, that is actually more of an energy mentality, because if you take the force times the distance, it's a certain amount of energy, right? You can also take pressure times volume change. What's that? That's also energy, right? So it's a bit of a conservation of energy mentality that I applied with the first case, whereas here I did more of a mechanics method. Okay. Cool. Any other questions? Excellent.